Okay, we're getting pretty close to the end of it, so let's get a wiggle on and finish off our topics on fuel metering devices. So, we finished talking about turbine fuel metering devices last lecture. We're going to take a look at a few auxiliary systems that are used to accomplish delivering fuel to the engine. So, we'll start with the turbine side of things. There isn't a lot to cover on the reciprocating engine side of things. We've already talked about the fuel injectors and that kind of thing, and a little bit about compensating pumps. So we're primarily going to focus on turbines here, and then work more on reciprocating engines in the lab as you start to tear some things apart. So first things first, what we're looking at right here, as mentioned in the previous lecture, we have engine-driven pumps that are used to deliver fuel to the turbine fuel control, or turbine fuel control rather. So we have our drive shaft right here along with the shear section. This shear section is designed to protect the engine in the event of a pump failure. So if we did have, for some reason, a jam in the pump where these gear pumps end up getting stopped or whatever the problem is, that drive shaft will shear and it protects the engine from damage with the stoppage inside the pump. Now, this incorporates an interesting design because typically we're used to seeing either a centrifugal pump or we're used to seeing a positive displacement vane pump or a gear pump or something like that. And this incorporates both. You hear this referred to sometimes as a dual or hybrid fuel pump. You see this exclusively with turbine engines. But the idea is we have fuel that comes in through an inlet, and we have this low pressure centrifugal impeller, which is providing our low pressure head that comes into the fuel pump. It also provides pressure that goes out to our heat exchanger, which is going to help with fuel icing. Once that comes back through a filter as well, we move in from the filter and we come to our high pressure pump gears, which send fuel out via these check valves to our fuel out area. We also have a pressure relief valve right here where if we overpressure, we schedule more than we need because it is a constant displacement pump. It'll allow it to come back to the inlet of the high pressure side. Everything works out pretty nicely, and these check valves prevent any drain back, allowing the pump to cavitate. And we did talk about two different items over here. We have this fuel air heat exchanger and we have this filter. So let's take a look at our heat exchanger first, which is right over here. So here is our heat exchanger. And what you'll notice about the heat exchanger is it looks an awful lot like any other kind of heat exchanger we have, either an oil cooler, a radiator, you name it, because it's doing the same job, except in this case, it's kind of doing it in reverse. So instead of having the air being cooled by what's flowing, or rather than having what's inside the passage being cooled by the air flowing over, we're actually trying to warm up what's flowing through, in this case, fuel, and that's being done by the air or the oil that flows through it. You'll see two versions. In this case, we have the air style, which is using high pressure bleed air. And the reason that we're using high pressure bleed air to run through these baffles to heat the fuel is because high pressure bleed air is going to be hotter. There's more compression, everything's pushed closer together, more friction rubs together, and the air is just hotter. In some cases, this can be used just exclusively as a temporary on-off system to prevent fuel icing. It may be used full-time to try to act as a preheating stage for the fuel because it helps to reduce ice with entrained moisture, and it also helps the fuel to atomize easier once it reaches the fuel nozzles if it's warmed up a little bit. So it kind of gets two for one, and then we get the extra added benefit of if we do need to use high-pressure bleed air for something, we have this outlet right here. If we need high pressure bleed air, but we don't want it to be excessively hot, we can pass it through this heat exchanger and then send it out to whatever you need to use it for. And it does the dual job of cooling down that high pressure bleed air, but also pre-warming the fuel so we don't wind up with any issues. And what you'll see over here is relatively similar to what you'd see with a oil cooler arrangement. So you have cooling fins and the shutoff valve right here. So this controls actual flow through the heat exchanger. And then we have a fuel temperature sensor. It could be located in the inlet to the cooler. It could be in some other areas, but basically we have our fuel that comes through. It goes through our baffles, right? So here's our fuel inlet, comes through the baffles, works its way through. We go past our fuel temperature sensor on the way out to our fuel outlet, back over to our filter. So that's a couple things that we look at. Let's take a look at our filter next. So one thing about turbine engine fuel controls is they are very, very sensitive to contamination. If there is really any particulate matter that gets in, it can potentially cause significant damage to the fuel metering device. And so we have to use micron filters to be able to remove any potential elements. So in this case, you're looking at something that's similar to what you'd see with, say, an oil filter or a similar type filter. We're going to have a in or a out to in flow with our fuel. So the fuel comes in through the inlet, it's going to build up pressure in the filter housing, and it's going to force it through the filter element to the inside, where it comes back out through the outlet and goes the rest of the way to the fuel control. If we do have too much pressure, to prevent this from collapsing, we have a spring-loaded relief valve that will allow fuel to bypass through. We may have a separate bypass route, depending on the design of the fuel metering device, to allow fuel to bypass the filter if it becomes contaminated and we clog the filter. Now, you may think, hey, didn't you just tell me that fuel metering devices are extremely susceptible and sensitive to contamination? Yes, I did. However, if you're going to pick one of the two, if we were going to ingest some particulate or just have the engine stop when the filter is clogged, then it's actually probably better off to just let the engine run for as long as it can. The most common thing that we're going to see that clogs these filters is ice. So as the engine operates, we get cool fuel that's flowing through. We create nice little spots on all of the filter material here for those ice crystals to start to seed and embed. And so they start to form, and then before long, we have a whole block of ice that's formed on our filter element, and it prevents fuel from being able to flow. In systems that are not full-time heating, either using a heat exchanger with bleed air or engine oil to preheat the fuel, then that will illuminate a indicator light in the cockpit showing that the fuel is now in bypass. Basically, the filter is clogged. We can double check our fuel temperature and cycle the switch that allows the fuel heater to work, which will in turn heat up the fuel and melt the ice, and everything works just fine. Pretty straightforward. But that's one version. We have this micron filter. The other type we have is this wafer disc type filter, which works fundamentally the same. We have these little thin discs, and you've probably seen these as well with some older style reciprocating engine oil filters. These are much finer than those, but it's not dissimilar from what you'd see with a wafer type filter or like a Cuno filter with a reciprocating engine oil filter. So same concept. We have a perforated core and all of these little wafer discs that stack on top of each other with a corrugated element and a spacer that goes in between to make sure there's space for the fuel to flow through and actually filter. But the idea is the same. We need to have a filter that protects the fuel metering device from being contaminated and potentially damaged. So as we look back over here, you'll remember we have our fuel inlet. We have this low pressure centrifugal impeller that's providing head pressure that goes out towards our heat exchanger, whatever type it happens to be. And then it goes through a filter and we come into our fuel metering device. Easy as that. All right, let's take a look at something else. We're going to go further down the line and we're going to talk now about how we actually get this jet A or jet B or whatever we happen to be using into the burner section to be used. So what we're looking at here is a example of what we call a simplex fuel nozzle. We'll describe the difference between a simplex and a duplex fuel nozzle here in just a minute. But what you'll see is relatively similar to what we'd see with a fuel injector in a reciprocating engine. So we have our fuel inlet right here. We have a check valve that allows the fuel to pass through, but does not allow any bleed back for introduction of foreign material or air into the fuel system. And we have a screen that the fuel will flow through out before it goes through our discharge orifice. Again, this is a metered orifice. It's designed to work with the pressure that's operating within the system, and it is there to atomize fuel and spray it into the burner section so it can be burned easily. Again, remember, the whole point of this is if we just have a liquid stream of fuel blowing into a burner, it's going to cause a couple issues. It's not going to burn very well. We can end up with hot spots and a few other things, but when we atomize it this way, we get a nice spray pattern that allows it to burn evenly. And that gets into why we have a duplex fuel nozzle. But let's take a look at this first. So with our duplex fuel nozzle, you'll notice we have primary fuel and we have secondary fuel. Now, what makes this interesting is when the engine is at idle, it has different flow pattern requirements for fuel. Basically, the velocity that fuel is discharged into the burner section is going to be proportional to the amount of air flowing through the burner section. As we increase the air significantly, getting all the way up to full power, then we're going to end up in a situation where we need a different spray pattern to effectively atomize fuel and burn appropriately. Now, what this does is it allows us to have basically two stages of fuel, our primary line and our secondary line, and it also incorporates an air screen. So we can either have air that's coming in from the atmosphere, or in a lot of cases, air that's taken from a bleed air source that's being injected into the end of this fuel nozzle that helps to atomize it further and discharge it. Now, one thing that we'll talk about when we look at these spray patterns, if we look right here, our secondary fuel manifold for low pressure is going to have a shorter, wider spray pattern because we're dealing with lower velocity airflow. As we go to our primary fuel manifold, we'll use both at the same time and we get a fuller spray pattern into the burner section. So the way that this works, we have our secondary path, which is our low speed or idle. It's going to move through. We move around the outside of this core, and we actually go, if you take a look closely here, we actually go through an outer passage that's not protected by a check valve or anything like that. It's just this outer passage that still picks up bleed air and allows it to discharge into a good spray pattern. Once we reach higher speeds, we open up the primary fuel line, and that primary fuel line flows through what we see more similar to just a straight up simplex nozzle, and it provides a narrower, higher pressure, higher velocity fuel spray pattern that goes into addition the secondary fuel source. So we have both primary and secondary operating at the same time. In order for this to work, though, what we need is a fuel control that is going to allow us to have the two kinds of fuel flowing through, a duplex control. Normally, this is going to get summarized, or it's going to get combined into what we call a pressurization and dump valve, or a P&D valve. I'll show you how that works real quickly. All that valve is doing is managing the fuel manifold at different stages the engine is running. So in this case, when the engine is just starting, right, we have our inlet from the turbine fuel control. So at low speed, as the engine just starts, or we're at low idle, we have this primary fuel manifold, which is opened up and allows fuel to flow through into our primary fuel manifold section, or however they have it arranged for the particular engine. So it's only going to connect that primary fuel manifold, and we pressurize that side of it. As we increase engine speed and we go to a higher demand for fuel, then that pressurization and dump valve is going to open to our secondary fuel manifold as well and pressurize that section as well, altering the fuel spray pattern we have, because now it's being discharged from both orifices. And then once the engine is brought to shut down and is closed off, both of those lines, primary and secondary, are going to connect to a drain line, and that can drain overboard off the engine. And the reason that we do that is because it prevents a few things. It prevents having fuel leak into the burner section, which can cause secondary fires or potentially damage or hotspot damage to the burner section. It prevents having issues that could occur to having fuel boil off or set inside of the manifold under high temperature, which can cause some weird issues like varnishing and that kind of thing, which ultimately it's all not really desirable. So as a result, once it's done running, we disconnect from the inlet, which would normally be flowing to our primary and secondary route, and we just connect both to a drain and send them both overboard. And that is your basics of how a P&D valve works. So that's the quick and dirty on how all these systems work with turbine engine fuel controls. Hopefully that makes a little bit more sense. One last thing I'd like to note over here is about our fuel flow meters. What you'll see in a lot of cases, especially if you start dealing in larger quantities of fuel, rather than just having a fuel quantity indicator, that doesn't necessarily give as accurate of a picture of how much fuel is remaining in an engine. And so what we can use is something like this, a fuel flow meter, which is going to measure the amount of fuel being burned in gallons or pounds per hour, whatever the metric happens to be. You'll see this very commonly with large turbine aircraft. You'll also see this with some smaller aircraft, and a lot of times this will all be combined into a device we call a totalizer. Now, the ones on larger aircraft tend to be a bit smarter. They may do things like actively take a look at the total amount of fuel that's available on the aircraft and then do the math for what that looks like with gallons per hour and produce something that looks like an effective range or effective flight time for the aircraft. With smaller, less complicated aircraft, it may be something as simple as a device that is hooked up to a fuel flow meter, and when the tanks are refilled or they're serviced up, you simply adjust how much fuel has been added into the system, and then it'll totalize for you how much fuel is estimated to be remaining based upon your gallon per hour burn rate. So it's actually a good way to improve safety and improve the information that's being brought to the pilot as the aircraft operates. That's what I got for you. Next one is going to be our last video talking a little bit about fuel system maintenance. So hope you've enjoyed it so far. We'll see you on the next video.